we will look at some of the interesting features of wireless communication networks, especially from the cellular communications point of view. First, the outline of today's lecture. Firstly, we will summarize what we have learnt in the last class. Then we will look at an interesting relationship between cell capacity and the reuse factor. The other interesting thing that we will learn today is traffic theory. How many calls can we handle? How many users can we support? How many calls will get blocked? How many calls will get delayed? All these are questions which will ultimately relate to the quality of service. Then we will talk about channel assignment strategies and finally handoff strategies. So, this is the brief outline of today's talk. Let us first start with summarizing what we did in the last class. We learnt that high capacity is achieved by limiting the coverage of each base station into smaller geographical regions called cells. This forms the essence of why within the limited frequency spectrum we can still provide service to hundreds of thousands of users. The same frequency or the time slots or the codes are reused by spatially separating the base stations. We ensure that the separation is such that the interference from these co-channel cells does not exceed beyond the acceptable limit. A switching technique called handoff enables a call to proceed uninterrupted from one cell to another. Today at the end of the talk, we will look at some handoff strategies. We also learnt that the hexagonal model for cells, even though universally accepted, is only of academic interest. In reality, the cells are not hexagonal, they are not circular, they are irregular in shape. Several things determine what is the shape of the cell, what is the size of the cell. However, when we do our basic calculations, for hexagonal cells, the reuse distance is given by d is equal to under root 3n times r, where n signifies the number of cells in a cluster, r signifies the cell radius is also equal to one side of the hexagon. We also learnt last time that the reuse factor is given by d over r. It is in fact the normalized reuse distance, normalized with respect to the cell radius r, and it is under root 3n. Please remember, this capital N is a design parameter. We can increase the value of n and it will lead to reduced interference. However, it will also reduce our capacity. So, it appears we need a handle on how to link this value of n to actual capacity of the cell and the capacity of the entire system. By capacity, we mean the number of users that can actually be supported in the whole geographic region. So, in this slide, let us have a look at the relationship between cell capacity and the reuse. Let us consider a cellular system with S duplet channels. Suppose each cell is allocated k channels and there are total n cells in the cluster. Remember, in the last class we saw that this value of n is an integer, can be 3, 4, 7, 12 and so on and so forth. It cannot be 6 because of the hexagonal cell shapes that we have chosen for our analysis. Whatever be the value of n, the total number of channels S is nothing but the number of channels in each cell times the n, the number of cells per cluster. If a cluster n is now replicated m times throughout the system, for example, if we have a 7 cluster cell, then over Delhi we can repeat it probably 20 times, right? So we can repeat it m times over the entire region of interest. The total number of duplicate channels available C is nothing but m times K. M is the number of times we repeat the cluster, K is the channels per cell, and N is the number of cells per cluster. Interestingly, K into N is S, which is a constant pre-allocated number of duplicate channels in the cell in the whole geographic region. What does S depend on? The total bandwidth given to the operator. So it is a constant. So we have an interesting relationship. C is equal to m times S, which is a constant. What do we conclude from this? If the cluster size n is reduced, that we have fewer and fewer number of cells in the cluster, then clearly we need more number of such clusters to cover the entire geographical region. So m must go up. If m goes up, the capacity C goes up, because C is equal to m times S. It could be intuitive also, but it is a very clear depiction here that yes, if I need to support more number of users tomorrow, I have to reduce my cluster size. But of course, there is no free lunch. There is a price to be paid for this. The price should come in terms of a co-channel interference level. If the cluster size is reduced, my frequency reuse distance, which is normalized to root 3n, that goes down, then my co-channel cell using the same frequency comes closer and my interference level must go up. Let us now look at some terms which we will use to understand how to characterize the traffic, how to say how many calls will go through or how many calls will get blocked, what do we mean by trunking, how do we use certain kinds of offered loads, right? So let us look at some terms and definitions. First of all, the setup time. Setup time is defined as the time required to allocate a radio channel to a requesting user. Please remember, there is a finite time that will elapse from the start of your request to you being actually granted the call. In fact, what is normally done is the number of users, the total number of users is much larger than the total available channels at any time. We believe that not everybody is going to talk at the same time. Yeah, this is the faith we have, and based on this faith, we always keep the number of users much larger than the total number of channels available. However, if someone requests for a call to be set up, we give one of the available channel, and for the entire duration of the time, the user gets to use the channel. After the call is over, the channel is returned to the channel pool. So this is the notion of trunking. You have a trunk which has several channels. So it's a pool of channels which the users can request for and use if available. It also means that sometimes when you make a request, you may not be granted a channel. You may be blocked or you may have to wait. So there are two parameters. You may have a probability of blockage and a certain duration of wait before you actually get to use the channel. Both these things are probabilistic, and sooner or later we will have to come up with formulae to estimate the time you have to wait or what is the probability of blocking that will take place. So setup time we have already defined. The other thing that we need to know is what is a blocked call. A call that cannot be completed at the time of request due to congestion. In literature, it is sometimes called a lost call. Lost call is lost revenue. I would not like to have many blocked calls. In fact, close to the New Year's Eve, you will find most of the mobile phones are facing the problem of blocked calls because too many people are trying to make the call. Holding time. Suppose you are lucky and you actually get into a conversation. You will use the channel for a certain duration of time. Now, some people talk longer than others, so there is a notion of average duration of a typical call. That is called the holding time. This holding time can be regulated by increasing or decreasing the cost per minute. So, the mobile companies can actually play around with this holding time by changing the tariff. Today, usually the tariff is going down because of competition, so holding time is actually increasing. The other interesting thing that we cannot do much about is the request rate. Please remember, we are in a very dynamic system. We do not know how many people are going to make that call. Okay? So, the average number of calls per unit time, usually represented by lambda, is the request rate. So, the units could be number of calls per hour. Typically, in an office environment, it could be 5 calls an hour. From home environment, it could be 2 calls an hour. If it is a call center, there may be 35 calls an hour or more. So, lambda changes from circumstances to circumstance. Traffic intensity is defined as the measure of channel utilization times. It is measured in Erlangs. Very soon we will define what is 1 Erlang. Load is actually the traffic intensity across the entire radio system. Please remember, all of these definitions are in the average sense. A channel kept busy for 1 hour is defined as having a load of 1 Erlang. Okay? So, that is the definition of 1 Erlang. So, we can measure the load in terms of Erlangs. We continue with our definitions. Something called as a grade of service or GOS is a measure of the congestion which is specified as a probability. Please remember, it should depend on many things. It should depend on the number of users who are trying to make a call and how long they hold the call once they get connected. So, there are 2 kinds of probabilities that we might be interested in. One is the probability of a call being blocked. If my service provider has designed his system for a higher probability of call blocking, tomorrow I might switch over to the competitor. However, the design of the system for very stringent call blocking probability will require them to reserve too many channels. So, we will look at an example today to see how the blocking probability translates to the number of users you can support. It is a direct one-to-one relationship and directly translates to revenue. The other probability that I am interested in is the probability of a call being delayed beyond a certain amount of time, right. So, beyond a certain amount of time, the user will also lose patience and probably give up trying to make the call. It is bad business strategy. So, we have 2 kinds of charts and associated formulae. One is called the Erlang B formula and the associated Erlang B chart, and the Erlang C formula and Erlang C chart, which tells us directly and quickly what are the probabilities vis-a-vis the number of channels available and the load. We will look at these. So, the average number of mobile stations requesting the service could be defined as lambda, as mentioned earlier. It is also called the average arrival rate. The units typically can be calls per hour. The average time for which the MS requires the service is called the average holding time, T. Typically, it is in minutes unless the call rates are very cheap. The offered load then is simply the product A is equal to lambda times t, and the units are lengths. Let us consider a small example. Let us have a cell of 100 users, and on an average I am getting 30 requests per hour, and every time a call is made, it lasts for a different interval of time. However, on an average a call lasts for 6 minutes. So this is a realistic scenario that I am talking about. Then the arrival rate in terms of requests per second is nothing but 30 divided by 3600 seconds. A channel kept busy for 1 hour, of course, is defined as 1 Erlang VC, and the offered load, which is A equal to lambda times t, is nothing but 30 divided by 3600 times 360 seconds, coming to 3 Erlangs. So I'd say that the load of that system with 100 mobile stations is 3 Erlangs. Interestingly, this number 100 has not come into the picture. I may have 1,000 users there, but at the end of the day I am interested in finding out how many requests they make per hour. If this is 100 users who are all teenagers and have a very busy social life, this will be more than 60 requests per hour. If this 100 mobile stations belong to a group of elderly people, it will be 2 requests per hour. So this number 100 does not carry any meaning, but this number of calls requested per hour does. Average arrival rate during a short interval t is given by lambda t. Now, probabilistically speaking, Poisson distribution could be assumed as the service requests, and the probability p as a function of n and t for n calls to arrive in an interval of length t is simply given by p equal to lambda t raised to power n divided by n factorial exponential raised to power minus lambda t. Remember, lambda t is of significance, it is the offered load. N is the number of calls to arrive in a length duration of t. Assuming mu to be the service rate and the probability of each call to terminate during the interval time t is given by mu times t, comes from the basic probability theory. Thus, the probability of a given call requires service for time t or less is simply given by s of t equal to 1 minus e raised to power minus mu t. So what do we do with these? We can predict probabilistically, right, that what is the probability of a given call requiring service for a certain time t or less. This t will come from other system design parameters. Continuing with our traffic theory, the probability of an arriving call being blocked is given by B, capital S of A. S is the number of channels in the group. Soon we will look at an example to see how we use this formula, but right now please remember A is the offered load, A raised to power S divided by S factorial multiplied by 1 over summation A raised to power K divided by K factorial. The other probability that I am going to use is the probability of an arriving call being delayed. It is given by this Erlang C formula. So these two Erlang B and C formulas will be used to find out. Please remember, the computations can get a bit expensive, so charts are already made of the pre-calculated values and they are known as the Erlang B chart, which relates nothing but the probability of blocking on one axis to the number of channels on another axis and A, the load, on the third axis. So it's a 2D graph, so there are a couple of parallel lines on the curve which kind of relate the three parameters: probability of blocking, the channels and the load. Given any two, you should be able to find the third one. Continuing with our traffic theory, we need to know something called the efficiency of the system. Efficiency is being defined as the traffic which is non-blocked divided by the capacity. Clearly, how many calls that I can handle divided by the theoretical limit of the number of calls that is possible to handle. And it is nothing but Erlangs into the portions of non-routed traffic divided by the number of trunks here. I am using this word trunks, it signifies a cluster of channels. And the trunking theory essentially relies that the number of users is much larger than the total number of channels available in the trunk. So, trunk is a bunch of channels. Let us now look at an example and see that these simple formulae can help you actually design a big system. So, here is our design space. Consider a very small cell with 2 channels. I have kept S is equal to 2 so that I can quickly put into that Erlangs B formula and I do not have to take in factorials of very large numbers. However, I have a lot of mobile stations into this small cell. Clearly, it is a bad design. Let us find out how bad is it, because I cannot have 2 channels supporting 100 users. But remember, the 100 user do not make much of an impact, how many calls they generate per hour does. So, continuing from the previous example where we had 30 requests per hour and average holding time of 6 minutes, let us see under these constraints how bad or good your system design can be. So, the offered load A can be calculated by lambda times T, a simple formula if the number of requests is given per hour and the call holding time is expressed in minutes, then it is requests times holding time divided by 60 is units in Erlangs. It is a simpler formula instead of converting everything by seconds. You can still do the other way around also. So, 30 calls per hour times 6 minutes per call divided by 60 is 3 Erlangs. So, that is the traffic being generated in this small cell, but a very ambitious kind of an environment with 100 users requesting 30 calls per hour. So, if you put these numbers where S is equal to 2 and A is equal to 3 in your Erlang B formula, you can simply calculate the blocking probability as 0.53. More than half the calls will be blocked. Not surprising, but not too bad also. If 100 people are generating 30 calls an hour, but there are only 2 channels, but the key factor is each call lasts only 6 minutes, then probabilistically just over a little half the calls are being blocked. So, whatever calls are being blocked will have to be rerouted. So, the total number of rerouted calls is 30 per hour times 0.53 is equals to 16 calls per hour have to be rerouted. Efficiency given by the earlier formula is the load times 1 minus the blocking probability divided by the total number of channels available is equal to 0.7. So, in this sad looking channel, I still have an efficiency of 0.7. Of course, this is not economically viable, nobody will accept this kind of a service. Please remember, to take this efficiency from 0.7 to 0.8 will require you to have some more additional channels. To take it from 0.8 to 0.9 will require you to do a much more effort. From taking from 0.9 to 0.99, it will take you much more effort. So, taking to that closer to 100% efficiency requires much more effort. Okay? Yes.
So what do we mean by rerouting of the call?
Okay, the question being asked is, what do we mean by rerouting a call? Suppose I try to make a call and I find, please try after some time. I get this recorded message. It means my call is blocked. Now, if I want to really make that call, I will actually wait for some time and redial. Again, 2 things can happen. I might get blocked again, or my call will go through. If my call goes through, my call was rerouted, in the sense that even though the first time it failed, I will have to, as a system provider, route that call sometime. So, if in the previous example 16 calls were blocked and these calls were really important to the users, they will make that call again and that traffic has to be handled at some time. Whether I borrow some channels from the neighboring cells or I pass on this call to my competitor is my problem. So, what we will do is at the later part of today's talk, we will see that sometimes you may allow one base station to borrow certain voice channels from the neighboring base stations.
So will it increase the interference, like it borrows the channels from the neighboring?
The question being asked is, if I borrow some channels on a temporary basis, does it have anything to do with interference? The answer is no. Interference right now has everything to do with how far is your co-channel cell is, right? And the planning has been done for that. So, if I borrow some channels from the neighboring cells, I am going to also borrow certain frequencies. What might offset is what is the frequency reuse distance from these specially borrowed channels. So, that might translate into some added interference. Question?
The total load should include the rerouted calls also.
Question being asked is, does the total load include the rerouted call? The answer is yes. There is a concept of offered load. That is, my system, which consists of the users, is offering a certain amount of load. In the previous example, that was fixed as 3 Erlangs. No matter what I do, the nature of the subscribers is such that they are together offering 3 Erlangs of load. Now, whether I can handle it or not is a different story. Fine. Here the blocking probability is 0.53. Typically, if I am to stay in business, I must offer something like 2% or less blocking probability. Fine. Let us look at some more examples to see how this blocking probability will actually affect the number of users I can support, and that translates to the traffic. So, let us look at another example. This time I am looking at a slightly larger system. The system has 100 cells, and this time each cell has 20 channels. Okay? The users are averaging 2 calls per hour, and every time they make a call, they only make it for an average duration of 3 minutes. So, I have changed some parameters here. It is a more realistic situation. The question I would like to know is how many number of users can be supported if the allowed probability of blocking is 2%. That is, on an average, out of every 100 calls that are made, 2 get blocked. I am allowing for this much. Then how many number of users can be supported? Clearly there has to be a link. So, from the Erlang B formula or a chart, the total carried traffic is 13 Erlangs. You can use these parameters to find out from that formula what is the load. So, the formula gives the blocking probability. Here you have been given the blocking probability, you need to do a reverse calculation. So, you need a chart. I have already plotted all the values. I look up the chart and find out that for a total carried traffic of 13 Erlangs, right, the probability of blocking is 2%, provided the number of channels is 20. So, what are the 3 parameters I have used to use the chart? 20 as the number of channels, blocking probability 2%, which gives me the third dimension 13 Erlangs. But per user traffic intensity is only lambda times t is equal to 0.1 Erlangs. This also we know how to calculate. So, the total number of users that can be supported in one particular cell is nothing but 13. The total carried traffic divided by 0.1 is equal to 130 users per cell on an average. So, ideally I can handle about 130 people per cell who are on an average making 2 calls an hour and each time they make a call, they talk for an average of 3 minutes. But my cell is not just one, but 100 cells to cover the geographic region. So the total number of users in my entire system is 13,000. It's not very good, because in a city like Delhi, this is peanuts. I need to do much better than this. I just cannot give service to 13,000 people. All right. Let us continue this example and see how things will change if my competition says, look, I will give you a much better quality of service, in this case called the grade of service. What does he advertise? He says, forget about a blocking probability of 2%. What if I promise you a blocking probability of 0.2%? 2 calls out of 1,000 will get blocked. So I am not annoyed each time I try to make a call during on peak office time and I say, please call back after some time. So let's look at the competitor. He works again with 100 cells to compare apples with apples. He again has 20 channels per cell. The users are the same. They are making 2 calls an hour on an average, lasting 3 minutes. But the question now is, how many number of users can be supported if the allowed probability of blocking is only 0.2%? So intuitively, what do you think? What should happen? Should I be able to support more number of users or less? Less. Fewer number of users can be supported. How much less? I'm talking about an order of magnitude difference in the blocking probability, going from 2% to 0.2%. Earlier I could support 13,000 users. Now will it be 6,000, 8,000, 10,000? Let's have a look at it. The answer again has to come from that Erlang-B chart. So from the Erlang-B chart, this time the total carried traffic is 10 Erlangs. Look, going from 2% blocking probability to 0.2% blocking probability, I have moved from a load of 13 to 10 only. What does it mean? That with the same traffic intensity per user as calculated before, equal to 0.1 Erlangs, the total number of users that can be supported per cell is now, it should be 10 divided by 0.1 is equal to 100 users only. 13 was the previous number, it should be 10. So only 100 users per cell, and overall I can have for 100 cells total of 10,000 users. So by going from 2% blocking probability to 0.2%, we have cut out 3,000 users in my whole system. So the question is, can I get additional users by promising to offer them 0.2% blocking probability as opposed to retaining my 2% blocking probability and supporting 13,000 users? Okay? So it's a business decision at this point in time. Where do you draw the line? Let us now look at another example. Consider a system with a total number of channels equal to 20 and the probability of blocking constraint as 1%. So on an average, 1 call in 100 gets blocked. What I would like to know is that how can I organize this number of channels? That is, what is the good way to trunk? How to group the channels? Well, I can do like this. If I have 20 channels available to me, I can keep all the 20 channels as it is, or I can divide the 20 channels into 2 groups of 10 each, called 2 trunks of 10 each, or I can take these 20 available channels and divide it into 4 trunks of 5 each. Right? Each trunk should provide me certain offered load. So let me rephrase the question. How should I use my 20 channels? And 20 is an example. If it is 200, it will make a lot of difference. So how do I use my 20 channels? Should I use it as it is, should I group it into two, so create two subsections and try to transport my traffic over these two sub-channels, subgroups of channels, or I can break up 20 into 4 and use these 4 trunks to send the channels. Please remember, the Erlang B chart is using one parameter as the total number of channels S, right? In the case of 4, for each channel or trunk which is offering a certain amount of load carriage can be totaled up as multiplied into 4, which will give me the total load. So let us look at this exercise. So divide the 20 channels into 4 trunks of 5 channels each. Now from the Erlang's B chart, the traffic capacity for one trunk consisting of 5 channels alone is 1.36 Erlangs. But I have 4 such trunks because I have 20 channels, so 4 times 1.36 gives me 5.44 Erlangs. However, if I look at approach 2, that is, divide 20 channels into 2 trunks of 10 channels each, for one trunk of 10 channel, we have a load 4.46. So the total capacity for 2 trunks will be 8.92. This is very interesting. I have almost a 60% increase going from 5.44 to 8.92. Let's go forward. Approach 3. Don't group them. Use 20 channels as such. So the traffic capacity for one trunk of 20 channels is 12 Erlangs. Way too much. It tells me it is better to make a larger pool than to subdivide the pools. So how we group the channels, what is the trunking methodology, will have a major impact on your system capacity. It's a very important point to be noted. So the allocation of a channel has a major impact on designing your system. So since channel allocation is of importance, let's look at some channel assignment strategies. A scheme for increasing capacity and minimizing interference is of importance, and that is what we are shooting for. Channel assignment strategies can be of 2 types. Either it can be fixed or it is dynamic. Fixed, of course, has an advantage that you plan it, you fix it, and you forget it. Dynamic, on the other hand, requires you to be adaptive. The choice of channel assignment strategy impacts the performance of the system, particularly how a call is managed when a mobile user is handed off from one cell to another. So capacity is one perspective and handoff is the other perspective. Later today, we should also look at some handoff strategies. So the first methodology is fixed channel assignment. Remember, the previous examples we did, we tried to fix certain number of channels per cell and then we did the calculations. So let us look at the fixed channel assignment strategies. Each cell is assigned a predetermined set of voice channels. Any call attempt from within the cell can only be served by the unused channels in that particular cell. If all the channels in the cell are occupied, the call is blocked, as we have seen, the user does not get the service. From earlier examples, we have also seen that what is the blocking probability, how can it be calculated, and how can it be linked to the offered load. In a variation of the fixed channel assignment, a cell can borrow channels from its neighboring cell if its own channels are full. This requires a little bit of intelligence, which neighboring cell to borrow from, and again it has some related interference issues. But still it falls under the category of fixed channel assignment. The other face of the coin is dynamic channel assignment. Here, contrary to the previous methodology, voice channels are not allocated to different cells permanently. Each time a call request is made, the base station requests a channel from the mobile switching center, which is the brain behind the whole thing. Remember, in more complicated cellular systems, there can be more than one mobile switching center, and there could be a head mobile switching center which controls the sub mobile switching centers. So we can have a hierarchy, but wherever it goes, the call request is made from somebody who manages the channels. The mobile switching center MSC allocates a channel to the requested cell using an algorithm. So it has to do some thinking. It has to have a strategy to allocate the channel. And what could be the possible things it has to consider before making a channel assignment? Well, the likelihood of future blocking, right? So if it has a choice of taking one extra channel from a cell in the Connaught Place area where the traffic is expected to be high but currently is not, versus a cell which is in the outskirts, then it will rather borrow a channel from the cell which is in the outskirts of the city, clearly. The frequency of use of the candidate channel, again it will relate to how much service we can provide in future. The reuse distance of the channel. Now, the channel must be such that it does not result in a lot of interference, because clearly when we borrow channels, we will cause some kind of unwanted interference, because it is not as per the frequency reuse plan. So I must assign a channel from a cell so that the resulting interference is not very high. And there are some other cost functions. I can have priorities built into it, some are preferred customers and things like that. Question?
What do you mean by the candidate channel?
The candidate channel,
The frequency of the use of the candidate channel.
yes, the second point, the frequency of use of the candidate channel. See, if my channel is being used, the request that I am making is being requested very many times, so it is a popular channel and that comes from a popular cell. So this should be taken into consideration, that there will be a request very soon for this channel again from this cell again, correct? So it should have an impact on the possibility of request from that set of channels.
But all channels are considered to be of the same type only.
Yes, the question being asked is, are all the channels considered to be of the same type only? Yes, here as a first level design, we are not differentiating between any one channel with respect to another channel. However, we can have variations. For example, some can be high priority channels. We can have resource reservations where certain preferred customers or who are paying a premium can always enjoy the luxury of non-blocked calls, that is, their calls will always go through. For example, suppose tomorrow I would like to use one of these channels not as voice but for data transfer, and I am a credit card company where I want none of the credit card verification to be blocked. Then I will reserve a chunk of channels which will never be blocked. So those are preferred channels. So calculations for those have to be done separately. In other ways, all the channels are same, identical, and no preference over one over the other, because the bandwidth is the same, the guard bands are the same, the interference issues are the same, so the channels are kind of equivalent. Continuing with the dynamic channel allocation, to ensure the minimum quality of service, the mobile switching center only allocates a given frequency if that frequency is not currently in use in the cell, or any other cell which falls within the limiting reuse distance. Remember, this reuse distance comes into the picture again, because if you give a certain channel, it should not create a higher level of interference. So, there is a minimum quality of service to be guaranteed. The dynamic channel allocation reduces the likelihood of blocking, thus increasing the capacity of the system. Please remember, we looked at the example of trunking. Fixed channel allocation is somewhat like trunking in the big scale. What we do is we group together certain number of channels and give it to different cells, and those are fixed, just like total of 20 channels broken up into groups of 5. So, 4 cells get 5 channels each. However, in dynamic channel assignment, I have the entire pool at my disposal, and as and when the calls come in, I can allocate a channel. So, the borrowing can inherently happen. Clearly, the capacity is much higher because the blocking probability will be much lower. The dynamic channel allocation strategies requires the mobile switching center to collect real-time data on channel occupancy and traffic distribution on a continuous basis. Please note that to make any of these algorithms effective, I must have true channel data. So, channel measurements are being done. It is not a big problem. All the calls which are being blocked can easily be recorded. The number of calls being generated can also be recorded. So, you can calculate the lambda, you can calculate the capital T, the call holding time, by monitoring on an average how many calls are being made and held during the call. Next, we come to the issue of handoff. Please remember, handoff has to be kept in mind as long as we are talking about mobile cellular services. Handoffs, so far we have seen, can happen because of two things. Firstly, you move from one cell to another cell while you are still on the call, and the second thing is you may be required to hand off one channel and go on to the next channel. So, there are two kinds of handoffs that take place. Let us look at the handoff required when you move from one base station to the other base station. So, when a mobile moves into a different cell while the call is in progress, the mobile switching center must automatically transfer the call to a new channel belonging to the new base station. So, new area, new base station, new channel. The handoff operation involves identifying a new base station and the allocation of voice and control signals associated with the new base station. All this must be done seamlessly. The handoffs must also be performed successfully, as infrequently as possible, and must be imperceptible to the user. Why should it be infrequently? Because each time I do a handoff, I use overheads. In fact, there are overhead channels used for handoffs alone. So, it requires computation on the part of mobile switching center, and if too many mobile stations are trying to hand off at the same time, the mobile switching center might actually get bogged down by the number of computations it has to do, because remember, there is an algo to be followed while doing handoff. So, it should be done as infrequently as possible. Let us look at the handoff region pictorially. So, what we intend to say in this slide is, by looking at the variation of signal strength from either base station, it is possible to decide on the optimum area in which the handoff can take place. So, the handoff region is not a discrete line that you draw, that you belong to base station 1 if you are on the left side of this line, and base station 2 when you are on the right side of this line. In fact, you have a region where you can hand off. Now, the size of the region is important with respect to the velocity of your travel. If you are traveling too fast, you have very little time to hand off, and so your call may get dropped during handoff. We do not want this. So let us look at it. Suppose we have base station I and we have another base station J. They are located at a certain distance apart. Now what we would like to do is have a mobile station which hopefully is now communicating with base station I, but is travelling towards base station J. During the process of travel, the signal strength from base station I starts dropping, and as it goes towards the base station J, it goes below a acceptable region. If you reverse the situation and make sure that the mobile station starts from base station J, but this time moves towards base station I, again the signal must drop as it moves away from base station J, but clearly goes closer to the base station I. So we have a parallel process where signal strength slowly goes down as you move away. Now these curves are very smooth because we are not taking into consideration the fading effects. Fading will be taught at the later part of this lecture series. But clearly we have two plots where power levels are going gradually down as you move away from base station I, and on the other hand going down as you move away from base station J. I would like to know what is the region where I can hand off. So for that I need to know what is the minimum sensitivity of my receiver, or even beyond that, what is the threshold till which I can still make a good call. So it is nothing but a line here, because on the y axis I have plotted the signal strength. So this horizontal line intersects the two curves at point 1 and point 2. Anywhere in between my mobile station can't hand off, but if it moves fast it might cross this region in 3 milliseconds. If it is a pedestrian, he may just be there for 30 minutes. So my handoff is much simpler for a pedestrian traffic than for a vehicular traffic. In this slide I have tried to show two circumstances, one where the handoff occurs successfully in the lower curve and one where it fails. So let us look at the lower curve first. Remember there are two regions, base station 1 and base station 2, and I am moving from left to right. Here is a depiction of the falling of the signal strength of the first base station, but very soon it locks on to the another signal strength of base station B. So there is a sudden jump in the power signal level because I am getting a much stronger signal from base station B. So I have locked on to the next one, hooked on to the next power level. So it is a successful handoff. On the other hand, here I keep on dropping and I am unable to latch on. Maybe there was no available channel or there was some other problem, and so I go below a certain level and I cannot operate beyond that. So handoff is made when the received signal at the base station falls below a pre-specified threshold. In deciding when to hand off, it is important to ensure that the drop in the signal level is not due to momentary fading. We will talk about fading later. In order to ensure this, the base station monitors the signal for a certain period of time before initiating the handoff. So it should not be a false alarm. I should hand off when truly the signal has dropped below a certain level and not a temporary drop. The length of time needed to decide if the handoff is necessary depends on the speed at which the mobile is moving. And since it is mobile communication, I cannot put restrictions on how fast they move. Some strategies of handoff. In the first generation analog cellular systems, the signal strength was measured by the base stations and supervised by the mobile switching center. In the second generation, we now know what is first generation and second generation. Those which use TDMA technology, mobile assisted handoff is used, called MAHO. In MAHO, every mobile station measures the received power from the surrounding base stations and continually report these values to the corresponding base stations. Handoff is initiated if the signal strength of a neighboring base station exceeds that of the current base stations. So, try to hook on to a stronger signal at any time. In this last slide for today, let us briefly look at what is the notion of soft handoff typically associated with CDMA systems. The code division multiple access SPET spectrum cellular systems provide a unique handoff capability. What is it? Unlike channelized wireless systems that assign different radio channels during a handoff, which we call hard handoff, the SPET spectrum mobile station share the same channel in every cell. Please note the difference, the same channel in every cell. The term handoff here implies that a different base station handles the radio communication task. The ability to select between the instantaneous received signals from different base stations is called a soft handoff. At this state, let us conclude today's lecture, and let me briefly summarize what we have done in lecture number 5. We started off with a brief recap and then looked at the cell capacity and how the reuse affects the cell capacity. Then we briefly looked at traffic theory, looked at the Erlang's B formula, the Erlang C formula. Then we looked at some examples as to find out how to relate the blocking probability with the offered load. Finally, we looked at channel assignment strategies and some handoff strategies. Thank you for your attention.